Hello, welcome to section 6.2, orthogonal sets. We're going to jump right into the definition of an orthogonal set so that we can get started right away. So a set of vectors in Rn is said to be an orthogonal set if each pair of distinct vectors is orthogonal, which we talked about in the previous section, illustrated here, whenever I does not equal j. So, for example, if I have this set of vectors, let's just call this A, B, and C for simplicity's sake. This set of vectors is not an orthogonal set because if I take the dot product or the inner product, so if I take, let's see, if I take A dot B, that gives me a dot product of 0. If I take B dot C, that gives me a dot product of 0. But if I take A dot C, that gives me a dot product of 4, telling me that each pair is not orthogonal. So if there is one pair that is not orthogonal, then it cannot be an orthogonal set. This leads to theorem 4. We will have an orthogonal set of non-zero vectors in Rn. So if that is the case, then S is linearly independent and is a basis for the subspace spanned by S. This theorem will come up in your homework, so make sure you are comfortable with that. An orthogonal basis for a subspace W of Rn is a basis for W that is also an orthogonal set. So this leads us to theorem 5, which we will use in many of the homework problems. So it says that the set is an orthogonal basis for a subspace W of Rn, and it says that for each y in W, the weights in the linear combination are given by this here, where j is equal to 1 up to p. So, in other words, we can represent this set as a linear combination where the weights are found by this formula here. So it depends on how many vectors there are in order to determine how many terms there are. And this is how we will approach it. So let's go ahead and look at our first example. So we have this set here of 3 vectors, and I am telling you that it is an orthogonal basis for R3, where U1, U2, and U3 are given. And I want to express vector y as a linear combination of the vectors in S. Okay, so because we have an orthogonal basis, we're basically using theorem 5 here. Okay, so what we need to do is we need to find all of the different weights. And the way we're going to do that is we're going to use this formula in order to find the weights. So by theorem 5, what we want to do is we will find y to equal, well, C1, so the weight of the first vector is found by taking y dot u1 over u1 dot u1 times vector u1, plus then the next one is y dot u2 over u2 dot u2 times vector u2. And then the final one is going to be y dot u3 over u3 dot u3 times vector u3. So this is what we need to find. So what we're going to do is we're going to focus on each one of these one thing at a time. So let's go ahead and find some of these. So let's start by finding y dot u1, or in other words, we're going to find the inner product of these two vectors. Okay, so this is from the previous section. So vector y in u1 will give us, let's see here, it'll give us 1 plus 4 plus 6, which is 11. Now I'm going to do y dot u2. I think it's easier to deal with vector y first. When I do this, I have 1 minus 2 plus 6. That's equal to 5. And then y dot u3 is negative 2 plus 0 plus 12. That gives me 10. Okay, now I am going to do the denominators. So u1 dot u1. So it's just this vector times itself. So 1 plus 4 plus 1 gives me 6. Then u2 dot u2 is 1 plus 1 plus 1. That's 3. And then finally u3 dot u3 is 4 plus 0 plus 4, giving me 8. So now I have all of the pieces for what I have written here, and I'm just going to plug those right in. So we end up with y equals, it's basically these fractions here, and you can reduce them. So 11/6 times u1 plus 5/3 times u2 plus, when I reduce 10/8, I get 5/4 times u3. And what I can do is, instead of writing u1, u2, u3, I can actually write them as vectors. So y is equal to 11/6 times this plus this and this. And there we have it. Now, depending on what you are asked for, you can go ahead and multiply this out and add those if needed. It just depends on what you're being asked for. And there you have it. Here is another example of the same type of problem. And it would be nice if you were able to give this one a try on your own. So again, we are given a set that I am telling you is an orthogonal basis. Because we know it's an orthogonal basis, we know that we can go ahead and use Theorem 5 just like we did before. We want to write this as a linear combination of the vectors in S. Okay, so we're going to do the same thing. We have 3 vectors, so I'm going to find y times u1. 18 plus 1 minus 8 gives me 11. Y dot u2 is negative 6 plus 2 minus 8, giving me negative 12. And y dot u3 is negative 3 minus 2 minus 28, which is negative 33. Excellent. Now we'll do u1 dot u1. So 9 plus 1 plus 1. We'll do u2 dot u2. 1 plus 4 plus 1. And then u3 dot u3. Ooh, fractions, that's fun. 1/4 plus 4 plus 49/4. Oops. That's 66/4, which reduces to 33/2. Okay, so by theorem 5, we can say that y is equal to, so it's the same formula that I wrote on the previous slide, and just for the sake of time, I'm not going to write that again. But remember that we have these fractions here if we set it up this way. Okay, so the first one is 11/11, which is 1 times u1, plus, then here I am -12 divided by 6. That gives me a -2, so maybe instead I'll write -2u2. And then I have -33/33/2. That gives me a -2u3. So there's that there. You can go ahead and write this with the vectors in place. Like so. And there you have it. So this here is a linear combination of the vectors in S. So now we're going to talk about orthogonal projection. And I know that some of you really like to see illustrations and you're visual and like to see pictures. I think rather than me attempting to draw these pictures, some of them are helpful to view in your book. I have one in this video, but it might be helpful for you to look at some of the pictures in the text. So here it tells us that the dot product can also be used to decompose a vector into separate orthogonal components. So it's basically us working backwards. So here, if we have a non-zero vector u in Rn and some vector y in Rn, we may want to write y, so this is a vector where we have two separate pieces that are orthogonal to u. So a lot of times people refer to this as y hat, and y hat is basically a vector times some scalar. So it's like a stretch or a shrink of some sort, and z is also a vector. And each of these are orthogonal to u. And remember, orthogonal is perpendicular. So we're going to let L denote a subspace spanned by u, then the orthogonal projection of y onto L is denoted by y hat, is found in the following way. So y hat is the same thing as saying the orthogonal projection of y onto L, which is also denoted in this way, is found by using this formula here. So it is very, very similar to what we have already found. So I want to remind you that z is some component of y that is orthogonal to u. So we talked about that on the other slide. There is a figure on page 342, so I think it's figure 2, that can kind of help you see what's going on. It kind of looks like this one, but there's some coloring in it, so I think it's a little bit better than this. And this is a typo, this should say y. So in Rn, we can visualize this projection. The vector y hat is the shadow of vector y on vector u. And we'll look at this later on in the text, but I want you to remember that orthogonal projections are right angles. So here is how this will be used. Okay, so it says let y be that vector and u be that vector. And what we want to do is find the orthogonal projection of y onto u. So this onto u. And it's from that definition 2 slides ago. So that's the first thing we want to do. Once we do that, we want to write y as a sum of 2 orthogonal vectors. One of the vectors will span in u, and the other one is orthogonal to u. Okay, so let's go ahead and get started. Now we only have 2 vectors here, so when I write my sum, I'm only going to have 2 terms. So I'm going to use that slide that we had previously that said y hat is equal to y dot u over u dot u times u. Okay, now this here is the projection of y onto u. So we have the projection of y onto u as well. Sometimes you'll have different variables, so be cautious of that. Okay, so this is, I'm just going to remind you, the orthogonal projection of y onto u. Okay, so the first thing we need to do is we need to find y dot u. So when we do that, we will have 28 plus 12, which is 40. And then I also need to find u dot u, which is 16 plus 4, so that is 20. So if I want to find y hat, which I do, I'm going to plug this into this formula here. I will have 40 divided by 20 times, times u. This is the same thing we did previously. So times vector 4, 2. So this gives me 2 times this vector. And remember, all this is a scalar. So I'm going to take 2 times 4 times 2 and end up with this vector here. So this here is the orthogonal projection of y onto u. So here's basically what that means. If I graph this vector, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, it's going to be here. So this is vector y. If I graph y hat, here's 8 and 4. So this is y hat. What we just found was this here. That is the orthogonal projection because it's perpendicular. Okay, so let's move on. So now we're moving on to part 2. And in part 2, we want to now write y as the sum of the 2 orthogonal vectors. Okay, so taking some baby steps to this, the component of y orthogonal to u is found by z. So this is z And so that is found by taking y minus y hat. So y is given to us. Y hat we just found. And this is equal to -1, 2. Okay, so if I want to find the sum of these two vectors now, so the sum of these two vectors is y, so y is equal to y hat minus y hat. So, let's see. So 7, 6 is equal to y hat is 8, 4 minus, I'm sorry, plus. This should be a plus. That's better. Plus -1, 2. There you have it. So I have an illustration here, but you can see something a little bit better on page 343. I believe it is figure 3. Now the last thing I want to mention is the information on this slide here. A set of vectors in Rn is said to be an orthonormal set if it is an orthogonal set of unit vectors. Now remember, orthogonal, the inner product is 0, and unit vectors, we talked about that in the previous lesson. So it goes on to say the simple orthonormal set is the standard basis for Rn. An orthogonal set can be made into an orthonormal set by normalizing each vector. So remember, that means giving them a unit length. This information, if you have forgotten what normalizing is, that comes from section 6.1, the previous section, page 334 in your text may be helpful. Now, I'm not doing any examples of orthonormal problems. There are 2 in your homework, so you will need to revisit some of this information if you have forgotten it from the previous section. But this concludes the information from section 6.2, orthogonal sets.